Can you see this fugacity of solutions? Can
No,
you
sir.
see it? No. Now?
Yes, sir.
Yes, sir.
Okay, so we started off, we first looked at fugacity of real gases, pure components. Then we looked at fugacity of liquids and solids. Now we're going to look at fugacity of solutions, because ultimately all systems which we encounter in chemical engineering are solutions. There will be at least two components. There's not going to be pure component, very rare. So we need to understand how to apply this concept to solutions, because that is our actual practical application. Our systems are going to be solutions, not pure components. Okay. So what we have seen is for pure fluids, dG is equal to RT dln F. This is what we derived. Where G is, what is G?
Gibbs energy.
Gibbs energy.
Yeah. So molar Gibbs free energy and fugacity is F, right? And the definition, by definition, fugacity of F by P is equal to 1 as pressure approaches 0 or low pressure. At very low pressures, the ratio of fugacity to pressure is equal to 1. Okay, that means fugacity is equal to pressure at very low pressures. That is ideal conditions. That's why we say for ideal conditions, fugacity is equal to pressure. But as we get non-ideal conditions or real gases, then we need to define fugacity. Okay, so similar to this one, this equation, we can define fugacity of a component I in solution. It can be gaseous, liquid, or solid. And for pure component, G is the what you call property which you use. It is partial molar or molar Gibbs free energy. But for solutions, we have to use partial molar property because that is more relevant for solutions. There are two components minimum. So we replace G by mu I, which is partial molar Gibbs free energy. So d mu I is equal to RT dln Fi bar, that is fugacity of component I in solution. Form is same, we just say by analogy, we write it for a component in solution similar to what we have for pure component. And by definition, like similar to this one, we define limit of fugacity of component I in solution divided by partial pressure of I when pressure is very low is equal to 1. Exactly similar to what we did for pure gases. And where mu I is chemical potential of I or partial molar Gibbs free energy, Fi bar is fugacity of component I in solution, and Pi bar is partial pressure of component I in solution. So that is similar, or by analogy we define it for solutions. Now if you look at ideal gas mixture, we know that Fi bar is equal to Pi bar because this is equal to 1, right? Fi bar by Pi bar equal to 1 when pressure is very low. That is ideal gas mixtures, right? And we know that all gaseous mixtures behave ideally when the pressure approaches 0 or very low pressure, you can say. Okay. So partial pressure is Pi bar is equal to Yi into P. This is Dalton's law. You have seen this in PC. You should remember all those things, right? So partial pressure of any component I in solution is equal to nothing but mole fraction of that component into total pressure. So if we take, because it is in gaseous solutions, this equation, and we know that effect of pressure on chemical potential we have seen before. Dava mu I over dava P at constant temperature and composition is equal to Vi bar, where Vi bar is partial molar volume of I in solution. We have seen what is partial molar volume also, right? So what we get is d mu I is equal to, replace, okay, Yeah, from here we get d mu I is equal to Vi bar into dP from this equation, from the effect of pressure on chemical potential. And if we compare equation 1 and equation 2, left hand side is same, so right hand side has to be equal. So what we get is d mu I is equal to RT d ln Fi bar, which we have seen here, is equal to Vi bar into dP. And from here we get d ln Fi bar is equal to Vi bar upon RT into dP. Now what we do is we do minus d ln Pi bar from both the sides because we want to get some form of the equation. So d ln Fi bar minus d ln Pi bar on this side is equal to Vi bar upon RT into P dP minus again d ln Pi bar. So what we get is d ln Fi bar by Pi bar, this minus will become here denominator, is equal to 1 upon RT if we take out common, Vi bar into dP minus RT d ln Pi bar. Any questions on equation 3?
Yes, sir.
Is there any question?
No, sir.
Okay. And we know that Pi bar is equal to Yi into P, so we can write ln of Pi bar equal to ln of Yi into P, or that is equal to ln of Yi plus ln of P. Right? So d ln Pi bar to d ln Yi plus d ln P from this equation. At constant composition, we always take constant composition, so Y is equal to constant. So when Y is constant, this is a constant ln of yi, and so derivative of that is equal to 0. So this term becomes 0, and what we'll get is d ln Pi bar is equal to d ln P, which is nothing but dP by P. Okay? Is this okay? Equation 4.
Yes, sir.
So then we substitute 4 and 3. This is d ln Pi bar. We substitute in this one, equation 3. We put dP by P, and what we'll get is d ln Fi bar by Pi bar is equal to 1 upon RT, Vi bar dP minus, this is RT d ln Pi bar, so dP by P. And this is nothing but 1 upon RT Vi bar minus RT by P, taking dP common into dP. So this is the equation we derive for Fi bar by Pi bar. As pressure approaches 0, Fi bar is equal to Pi bar. That's what by definition we have said. At low pressures, viscosity of component I in solution is nothing but partial pressure of component I. So if we integrate this equation 5 from 0 pressure or low pressure to the desired pressure, and the left hand side is ln Fi bar by Pi bar. So the limits will be at low pressure Fi bar is equal to Pi bar, this is what it is, and at any other pressure viscosity is equal to Fi bar. So we get d ln Fi bar by Pi bar, integral of that from P1 Pi bar to Fi bar is equal to 1 upon RT integral 0 to P Vi bar minus RT by P dP. Okay, any questions on this?
इक्वेशन 4 दिखाए ना ऐसे.
Equation 4, ये equation 4 है. d ln Pi bar is equal to dP by P. This we have put here in equation 3. d ln Pi bar, so this becomes RT into dP by P.
सर लिमिट्स का एक बार बताओ ना फिर से.
Limits का, okay. So we are integrating from low pressure to any pressure. You know, this could be low pressure is 0. We are taking as 0. This could be 5 atmosphere, 10 atmosphere, जो भी pressure है, और system का pressure जो भी है. We want to find out what happens when the system goes from low pressure when it is ideal to any pressure when it is say non-ideal, right? So at low pressure we have seen that Fi bar is equal to Pi bar. तो यहाँ पर क्या है, लिमिट Fi bar का रहेगा because Pi bar is constant there. So we get limit जो lower limit of Fi bar is Pi bar at low pressure, at zero pressure is Pi bar, and at any other pressure, it could be high pressure, the fugacity is Fi bar, which we have to find out. Actually, this is what we have to find out. This we know. All things are known. Vi bar is known, RT by P is known, but Fi bar is unknown. So we need to find this out. ठीक है?
Okay, sir.
So if you put this is integral will be ln of Fi bar by Pi bar from Pi bar to Fi bar is equal to 1 upon RT integral 0 to P, again same thing, Vi bar minus RT by P dP. So what we will get is, when you put the upper limit, it is ln of Fi bar by Pi bar, lower limit will be ln of Pi bar by Pi bar. What is ln of Pi bar by Pi bar?
0.
0, right? So that's why I put nothing here, minus something, minus nothing. So this is equal to, this right hand side is same, and when we define this as Fi bar by Pi bar as fugacity coefficient, right? By definition, this is fugacity coefficient, ln of phi I bar. We have defined for pure component phi I, Fi by Pi. So for solution, it is Fi bar by Pi bar is equal to phi I bar, fugacity coefficient. Any questions on equation 6?
सर
Yeah, बोलो.
सर अगर कंपोजिशन कांस्टेंट नहीं लिया तो फिर क्या होगा? मतलब
See, we are always looking at change of, see, we are going from say ideal condition to non-ideal condition, right? We are saying कि अगर हमने ideal, we start with ideal condition because our basis or standard state is ideal condition always. So we always say कि अगर ideal condition लिया हमने starting में और उसको non-ideal किया तो क्या होगा? Composition change we'll see later. Let's not worry about that now. Right now, let us see कि what happens when some gas or solution goes from ideal condition, ideal to non-ideal. You cannot change too many things at the same time. So you do one at a time. Otherwise, you complicate the matter. Composition भी change करेंगे because you see when you take derivative, you say partial what derivative of what you call G with respect to T, keeping pressure and composition constant. If you change two at a time, then mathematics will also be complex. Doesn't work that way. So we always say effect of one variable क्या है? एक change किया तो क्या होगा? Two variables change at the same time, then it goes to design of experiments. It's very complex. Yeah, that's why we always say एक ही change करने का. Because when you say derivative of this with respect to this, right? G with respect to temperature or G with respect to pressure, keeping composition constant. We don't change the composition because if you change the composition also, then it becomes very complex. Mathematics itself will be very complex. So let's not worry about composition change किया तो क्या होगा. We'll see that later.
ओके सर.
Right now we are looking at when you go from ideal conditions to non-ideal conditions. That's what we are saying here, right? From low pressure to any pressure, high pressure, if you go, what happens to fugacity? That means we are going from ideal conditions to non-ideal conditions. What happens? How does the fugacity change? You know, at ideal conditions, fugacity is equal to partial pressure. So at high pressure or any other pressure, what is the value of fugacity? ठीक है? And we have seen fugacity पे essentially we have seen is basically the effect of pressure which we have seen throughout. Pure component के लिए pressure का effect देखा था हमने throughout. So let's stick with that for the time being. Let's see later क्या होता है. Okay? That we'll see later. Composition का effect क्या होता है. Okay, so phi I bar is viscosity coefficient of I in solution, which is defined as phi I bar is equal to Fi bar by Pi bar, which is nothing but Fi bar, and Pi bar is Yi into P, mole fraction into total pressure. Okay, so now if we take a mixture of ideal gases, you can write PV equal to nRT as PV total is equal to N1 plus N2, all the moles of all the components, into RT. Right? So if you look at this one, VI bar is partial molar volume, because we need to put here, right, VI bar. In this equation 6, we need to substitute for VI bar. That's why we are doing this. So if we take ideal gas, and from this we find out VI bar, that is nothing but double VT double by double Ni at constant temperature, pressure, Nj not equal to I. See, we always change one at a time. यहाँ पर सिर्फ composition of I change किया. We don't change total composition, keeping temperature, pressure constant. Right? So what we'll get is RT is constant. यहाँ पर N2 की जगह पर 0 आ जाएगा, N1 की जगह पर 1 आ जाएगा, यानी इसे डबा N1 by डबा N1 into RT divided by यहाँ पर P. So VI bar is nothing but RT by P for ideal gases. ठीक है? Any questions on 8? No. Okay. Let's go. We have to substitute this one in this equation now. तो क्या मिलेगा हमारे को? Substitute 8 and 6. What you get is right hand side is 0, because VI bar is equal to RT by P, so this becomes 0. So what you'll get is double ln Fi bar by Pi bar is equal to 0. So ln of Fi bar by Pi bar is equal to 0. So the right hand side is Vi by RT minus Vi by RT. So this is 0. There's nothing but ln of Phi bar, and that is equal to ln of Fi bar minus ln of Pi bar is equal to 0. That means ln of Fi bar equal to ln of Pi bar. That means Fi bar is equal to Pi bar. Right? This is what we have. We start with definition, but you can show it this way also. That means for ideal gas mixture, the viscosity of component I in solution is nothing but its partial pressure, which is equal to mole fraction into total pressure. This is by definition, but now we have shown it from equation that this is applicable for ideal gas mixture. Viscosity of a component in a solution, in a mixture of ideal gases is equal to partial pressure of the component in the mixture. Okay? Any doubts on this?
लास्ट स्लाइड है
क्या ये बताने का?
सर इक्वेशन 8 तक दिखाऊं जरा.
हाँ उससे पीछे
क्वेश्चन 8. ओके, इक्वेशन 6 समझाना. इक्वेशन 6 and 7.
हाँ सर 8.
8 we are looking at, we are saying कि ideal gas रहेगा, so we can write PV is equal to N1 plus N2, or total number of moles, into RT. Now if we take, we want to find out VI bar, because this equation has VI bar in this one. So we need to find out the equation for VI bar for ideal gases. VI bar is nothing but double VT by double Ni at constant temperature, pressure, keeping other compositions constant, other moles constant, Nj not equal to I. So if we take this derivative, on the right hand side it is N1 plus N2, etc. So if I take with respect to 1 N1, it is ये 0 हो जाएगा, ये 0 हो जाएगा, we get 1 double N1 by double N1, that is 1 into RT. So similarly ऐसे सब करेंगे तो we get RT by P, and ये जो P है इधर से नीचे आ जाएगा. So what you get is VI bar is nothing but RT by P. This is for ideal gas. ठीक है, equation 8. Well, I am taking derivative with respect to Ni. So I can take, suppose I say double Vt, if I want V1 bar, कंपोनेंट 1 का निकालना पार्शियल मोलर वॉल्यूम, तो डबा VT बाय डबा N1 कांस्टेंट टेम्परेचर कांस्टेंट प्रेशर NJ नॉट इक्वल टू 1 आएगा, राइट, एंड दैट मीन्स NJ इज कांस्टेंट फॉर N or component 2, component 3, component 4, etc. If I take derivative with respect to 1, so it is dava n1 by n1, dava n1 by dava n1, that is 1, ये 0, ये सब constant है, right? So derivative 0 रहेगा into RT. So similarly, if I take component 1 I, any component I, I'll get same thing, RT, and ये P इधर से आ जाएगा. ठीक है? समझा गया इक्वेशन 8?
Yes, sir.
Okay, so now we'll put this VI bar is equal to RT by PE, or if you put it here, it's nothing but integral becomes 0. This VI RT by P minus RT by P, this is 0. So what we'll get is ln of Fi bar by Pi bar is equal to 0. This is nothing but fugacity coefficient. So we get ln of Fi bar minus ln of Pi bar is equal to 0, or ln of Fi bar equal to ln of Pi bar. That means Fi bar is equal to Pi bar, which is nothing but mole fraction into total pressure. This is for ideal gas mixture. When we're considering ideal gases, it's a mixture of ideal gases. Because by definition we said that, right? We said this right at the beginning. We said this right at the beginning, right? By definition, limit of Fi bar by Pi bar when pressure tends to 0 is equal to 1. That means for ideal gases, Fi bar equal to Pi bar. Now we have shown the same thing from that equation for fugacity. Right? We have shown the same thing by equation, by derivation. Okay? The fugacity of a component in mixture of ideal gases is nothing but partial pressure of the component in the mixture. Okay? So let's move forward. So let us see how we apply this. This is all theory. Now we need to actually apply. Problem solve करने का है तो अपने apply करना पड़ेगा. So we define Lewis-Randall rule, which is applicable for gaseous mixtures. So calculation of fugacity of gaseous mixtures using equation 6 is difficult since Vi bar is not measurable. We have seen this. अभी ideal gas के लिए लगाया हमने, निकाला, right? But for real gases it's going to be difficult, this equation, because Vi bar is not measurable. We always calculate it, right? हमने देखा था partial molar volume कैसे calculate करने का. It's always a calculated property. You don't measure it. You can measure molar volume, but you cannot measure partial molar volume. You always calculate it. So for mixture it is difficult. So now we need to see some other way of doing it. So therefore we use ideal solution model. What is the ideal solution model? A gas mixture formed without any volume change on mixing. Right? So when we started at the beginning, we saw partial molar volume, and we saw that partial molar volume and molar volume relation क्या है? Does anybody remember? Molar volume is for pure component. Partial molar volume is for a component in solution. Right? And हमने एक example भी किया था. कौन सा example था? Problem solve किया था ना एक. Does anybody remember the problem?
सर वो अल्कोहल और वाटर का किया था.
Alcohol water, right? So alcohol water का problem किया था. उसमें क्या देखा था हमने? What did we see? What was the conclusion?
सर वो वॉल्यूम कम होता है.
Volume कम होता है, right? So if you want to make 2 cubic meters of solution of say alcohol and water, then we need more than 2 cubic meters of pure components, right? Total volume 1.0 something for ethanol, 1.0 something for water. ज़्यादा लेना पड़ता है बिकॉज वॉल्यूम कॉन्ट्रैक्शन होता है ऑन मिक्सिंग. कभी कभी बढ़ भी सकता है बट दैट इज वेरी रेयर. नॉर्मली वॉल्यूम रिड्यूस होता है. बराबर. So when we say ideal solutions, we are assuming that there is no volume change on mixing. Real solutions, there is always or most of the time it is volume change on mixing. Rarely होता है when the molecules are similar, then there may not be any volume change on mixing. But generally, when we mix two components, there is some volume change. It could be positive, it could be negative. Right? So now we say again, just like we define ideal gas. Ideal gas is practically होता नहीं है कुछ, because most of the systems are at higher pressure. You can apply ideal gas only at low pressure. So similarly for solutions, we define ideal solution model, which means that if you mix two gases, A and B, there's no volume change on mixing. That's how we define ideal solution model. In reality, there's nothing like ideal solution. But yeah, that's approximation. जैसे बोला ना, models are there. एक approximate model रहता है, एक accurate model रहता है. Approximate models are useful where you don't want very accurate data. You use a rigorous model or more complex model when you want more accurate data or prediction. So different models have different uses. Some are useful in some situations, some are useful in some other situation. So we define ideal solution model, which is nothing but a gas mixture formed without any volume change on mixing the components. So if I mix two components, there is no volume change. That's what I say. If there is no volume change on mixing two components, then we can call that as an ideal solution model. समझा क्या? This is definition. Because we always say, जैसे हमने standard किया, वो definition है. We define that because it is always related to that we find out variations. So now we are defining ideal solution model क्या होता है. Without test पे किसी को?
No, sir.
No doubt. Let's move on. And what is Avogadro's law? याद है Avogadro's law किसी को? किसी में पढ़ा था हमने. I think you studied in chemistry also, right? What is Avogadro's law? Dalton's law, Avogadro's law. याद रहना चाहिए आप लोगों को. They are not to be forgotten. What is Avogadro's? रितेश.
हाँ सर, मैं वो पूछना था कि सर आइडियल सॉल्यूशन में अगर हम दो सॉल्यूशन ऐड कर दे मिक्सचर, तो उसका वॉल्यूम घटता नहीं है क्या?
That is definition. We are defining. See, ideal condition. जैसे ideal gas बोला, कैसे define किया हमने? PV equal to RT, right? Some basis, right?
Yes sir.
चार्ल्स लॉ लिया, बॉयल्स लॉ लिया, कंबाइन किया हमने, आइडियल गैस लॉ को डिफाइन किया, बराबर. एंड देन वी सेड कि आइडियल गैस लॉ इज एप्लीकेबल ओनली एट लो प्रेशर्स. बिकॉज हाई प्रेशर किया तो नॉन आइडियली आ जाता है. अट्रैक्टिव फोर्सेस, रिपल्शन फोर्सेस आता है, वॉल्यूम ऑफ द कंपोनेंट्स बिकम सिग्निफिकेंट. सो ऑल दोस नॉन आइडियलिटीज आर देयर. Similarly, we are defining an ideal solution model because we want to actually start from simple cases. So always start simple and then see what is the complexity. कभी भी ऐसे रहता है. You always try to solve a simple problem. Then you say ठीक है, अभी complex problem कैसे solve करने? Because understanding के लिए simple problems are easier to understand what is happening. So we define ideal solution model. What is it? क्या definition दिया हमने? आइडियल सोल्यूशन मॉडल का क्या डेफिनेशन दिया अभी? रितेश.
हाँ सर.
क्या डेफिनेशन दिया हमने आइडियल सोल्यूशन मॉडल का?
वही समझना था, इसलिए पूछ रहा था.
By definition, we are saying that when you mix two components, two gases together, there is no change in volume. That is the definition of ideal solution model. In reality, it may not happen. We are saying this is the ideal condition. जैसे आइडियल गैस है, वी आर सीइंग आइडियल सॉल्यूशन। ठीक है।
Yes, sir. Yes, sir.
So we are looking at Avogadro's law. Who can tell me what is Avogadro's law? Stroke.
Total volume is equal to
Huh?
total volume of a mixture is equal to volume of each summation of volume of each component.
Yes. Good. Who was that?
Pratiksha More.
Good. So what is Avogadro's law? We have seen this before. आपने पढ़ा होगा बहुत बार. Gas mixture that follows Avogadro's law is an ideal gaseous solution, right? What is Avogadro's law? The volume of the mixture is a linear function of mole numbers at fixed temperature and pressure. That means if I take two gases and mix them, or 1 mole of each, then total volume is nothing but volume of each component. That's what you said. V total is equal to summation of Ni Vi. This is Vi is molar volume of pure component. This pure component volume is total volume of the mixture. This is Avogadro's law, and that's what we are saying. यहाँ भी वही बोला हमने आइडियल सोल्यूशन मॉडल में विदाउट एनी चेंज इन वॉल्यूम. तो हमने जो प्योर कंपोनेंट वॉल्यूम लिया, multiply with number of moles which you are mixing. If you do that and take the summation of all the components, we should get total volume. Right? That means we are saying Avogadro's law is applicable for ideal gaseous solution, not for real gases. ठीक है? Any doubts on Avogadro's law?
No, sir.
Okay. So if we take this thing by definition and we want to find out Vi bar, what we'll get is double Vt by double Ni at constant temperature, pressure, Nj not equal to I. What we'll get is only Vi. Right? Because if we take this double Ni by double Ni, which is 1, so we get Vi. That means for ideal solution model or ideal solution gaseous mixture, partial molar volume is equal to molar volume. We are saying that there is no change in volume. कब होगा? When partial molar volume is equal to molar volume, then only there is no change in volume when you mix two components or more than two components. ठीक है? इक्वेशन 9 में डाउट है किसी को? Any doubts on equation 9? जो हमने किया था पहले प्रॉब्लम, we saw that partial molar volume was different from molar volume. That is why there was a reduction in volume. यहाँ पर what you're saying is, if there is no change in volume, that can happen only when the partial molar volume is equal to molar volume. If they are different, then we have to see क्या होगा. वो देखा हमने पहले भी कैसे कैलकुलेट करने का. ठीक है? And for ideal gas, if you say Vi is nothing but RT by P. ठीक है? Any questions so far?
So total volume will be equal to RT by P.
हाँ, यहाँ पर क्या आना चाहिए? This should be Pi. Yeah, right. You're right. Should be RT by Pi. Partial pressure आना चाहिए. ठीक है?
Yes, sir.
Okay, so if you take okay, equation 6 हमने ये दिया था, ln of Fi bar by Pi bar is equal to 1 upon RT integral 0 to P Vi bar minus RT by P into dP. for component I and gaseous mixture. For pure component, you can write similarly. Ln Fi by P is equal to 1 upon RT integral 0 to P Vi instead of Vi bar, because Vi bar is equal to Vi minus RT by P dP. Okay? And this we have seen, what is this? Vi minus RT by P. What is Vi minus RT by P?
0.
0. I'm not saying it is ideal gas. I said pure component, real gas.
तो टोटल वॉल्यूम
It is equal to alpha. ये हमने देखा था पहले. Alpha is what?
Residual volume.
Residual volume. हम पहले derive किया था, right? One way of determining partial molar volume, or I think partial molar volume था by residual volume, right? So this is nothing but alpha for real gases. For ideal gases it is 0. But for real gases it is RT alpha into dP. So if we take, now take 6 minus 10, equation 6 minus equation 10, let's see what we get. What we'll get is ln Fi bar by Pi bar minus ln Fi by P equal to 1 upon RT, and another integral is Vi bar minus RT by P minus Vi minus RT by P. ठीक है, RT by P कैंसिल हो जाएगा, and what we'll get is ln of Fi bar by Pi bar, and this is minus, उल्टा हो जाएगा, P by Fi is equal to 1 upon RT integral 0 to P Vi bar minus Vi into dP. ठीक है, इक्वेशन and you know that Pi bar is nothing but Vi into P, more fraction into total pressure, and you put it here, what you get is ln of Fi by Vi into P by Fi is equal to 1 upon RT integral 0 to P Vi bar minus P Vi into dP. So pressure cancel हो जाएगा, what you get is ln of Fi bar by Vi into Fi is equal to same thing, right hand side. ठीक है, इक्वेशन 11. So in equation 9 we have seen Vi bar is equal to RT by P is equal to Vi. So what we put is ln Fi bar by Fi is equal to 0, right hand side, because Vi bar is equal to Vi. This Vi bar for ideal gases it's 0. Sorry, Vi bar is equal to Vi, ideal solutions, right? We have seen this equation 9. For ideal solutions, forget about this part. Vi bar is equal to Vi. And if we substitute in this equation, we substitute in this one, Vi bar is equal to Vi. For ideal solutions, this right hand side becomes 0. And what we'll get is ln of Fi bar by Fi is equal to 0. Equation 12.
सर फिर हमने वो रेसिडुअल वॉल्यूम कंसिडर करते वक्त आइडियल क्यों नहीं कंसिडर किया?
Residual volume for ideal is 0.
हाँ, तब हमने प्योर कंपोनेंट कंसिडर किया था. अब लास्ट इक्वेशन में हमने आइडियल कंसिडर किया.
सर वो इक्वेशन 11 जरा फिर से बताना, वो अल्फा के आगे.
अल्फा के आगे So just to show you कि हमने पहले किया था. We are not using this alpha anywhere, but we are just saying कि ये this was what we had seen before. What we are using is for pure component real gases. See, ultimately what we are trying to do is we are trying to find out Fi bar, that means in solution. How do you find out Fi bar from pure component? Fi bar is for component I, fugacity of component I in solution. Now we are trying to relate it with fugacity of pure component. Because we know pure component कैसे easily कर सकते हैं determine. Solution का is more difficult because ultimately your what objective is to find out fugacity of solutions or components in solution. And we are trying to correlate with pure component solution. What is the relation? That's why we took the difference between the two. Solution का और pure component का. Right? 6 was for solution. This is for solution. And 10 is for pure component. And now we are trying to correlate ये जो fugacity of component I in solution है. How is it related to fugacity of component pure component I? Because pure component determination is easier. The solution is more complex. ये इसको भूल जाओ. This is just to show you कि क्या था ये. But what you are doing is you are just taking 6 minus 10 and trying to find out, can we find a relation between fugacity of component I in solution with fugacity of pure component. The objective is what? Objective is how do I find out fugacity of component I in solution. ये ऐसा क्यों नहीं लिया, वैसा क्यों नहीं लिया? Yeah, you can take that also. But is that going to help us solve the problem? Is that going to help us find the fugacity in solution? Yeah, ultimately our goal is पहले fugacity of pure component निकाला, fugacity of solution निकालना. Solution कैसे निकालेंगे? From pure component. Yes.
In equation 10, should it be ln Fi by Pi or P?
It is pure component. Pure component there is no Pi. Pure component there is no partial pressure. It's total pressure only. समझा गया? We talk about pure component. We don't talk about partial. Partial pressure is equal to total pressure. And there's a mixture. Then only we talk about partial pressure. Because y is equal to 1, right? I take y pi bar, pi is equal to y into p, right? Y equal to 1. So p is equal to pi. If you want to talk about partial pressure.
Then Fi क्या है?
Component I का fugacity ना? Fi is component I का fugacity, pure component I. When you say pure component, there is no partial pressure concept in pure component. है क्या? होता है क्या partial pressure?
No.
Even if I write it as obviously by analogy, if you want to say कि Fi bar by Pi bar, so I should write Fi by Pi. Okay, I write Pi. What is Pi for pure component?
P.
Correct? And that's why we have taken, ultimately our goal is to find out a fugacity of solution of component in solution from fugacity of pure component. That's our objective. That's why we are doing all this. If हमने solution का fugacity लिया, component I in solution and component I in pure state. And then we are trying to correlate these two. तो माइनस किया हमारे को ये मिला इक्वेशन vi bar minus vi, and what we are saying now is just substitute this pi bar is equal to yi into p. What we'll get is ln fi bar by y into fi is equal to right hand side is this equation 11. Now this is applicable. You have not made any assumption of real gas वगैरह, ideal gas here, right? is for real gases. But now we say ideal solutions, Vi bar is equal to Vi. Now we have set that assumption now. This for all solutions. Now we say ideal solution के लिए क्या हो जाएगा? This Vi bar is equal to Vi. तो ये 0 हो जाएगा. For ideal solution, now this is the equation. Because we always try to simplify it, come down to basis. Ideal solution के लिए क्या होता है? Then we'll see non-ideal के लिए क्या होता है. ठीक है? Equation 12 any difficulty? Any questions on equation 12? That's why we defined ideal solution model. Ideal solution model define किया तो उसके लिए हम कैसे निकालेंगे? So first we find out for ideal solution what is fugacity of component I in solution. Then we'll see non-ideality का कैसे करने का handle करने का. Just like we define ideal gases and then we'll say कि ठीक है ideal gas के लिए ये है तो real gas के लिए क्या होगा? So we define what do you call Tank-Robinson equation, SRK equation, RK equation, right? Van der Waals equation. Then we go from ideal to non-ideal. Now we are saying अभी ideal solution के लिए define करते हैं. Then we'll see how to handle non-ideal solutions. We always go from basic or simple things to complex things. ठीक है? So if you take this equation 12, what we'll get is Fi bar is equal to Yi into Fi because this is equal to 0. That means this is equal to 1. Fi bar by Yi Fi is equal to 1. That means Fi bar is nothing but Yi into Fi. Just like we say Pi bar is equal to Yi into P. करते हैं कि नहीं? Partial pressure is equal to Yi into P. So partial pressure of component 1 is nothing but mole fraction of component 1 into total pressure. Now we are saying fugacity of component I in solution is equal to mole fraction of component I into pure component fugacity. So now we understand why we are doing all these things. We are trying to find out fugacity of component I कैसे निकालने का from pure component. And this is called Lewis-Randall rule or Lewis fugacity rule. Any questions on equation 13? No questions? Doubts नहीं है? Question नहीं है किसी को? So Fi bar is nothing but fugacity of I in ideal gaseous solution. This is ideal solution, right? And Fi is fugacity of pure I at the same temperature and pressure. So now we are relating fugacity of ideal solution with fugacity of pure component. If we can find out Fi, we can find out Fi bar because mole fraction is normally known. You know that.
सर
Yeah.
सर वो रूल हम टोटल के लिए नहीं लिख सकते क्या?
Total क्या?
मतलब टोटल कंपोनेंट के लिए ये आई के लिए था ना Fi bar equal to
Fugacity is for component. There is no fugacity of total solution.
ओके सर.
There is no fugacity of total solution. Fugacity of each component रहता है. Pure component में रहता है. When you have a solution, when you have mixture, there is fugacity of each component is separate. When it is pure component, yes, then there is a fugacity of component because there is only one component. But when you have 2 or 3 components, then each component will have its separate fugacity.
यस सर.
Okay, so what you have seen is Fi bar is equal to Y into Fi for ideal gaseous solutions, and if is ideal gases के लिए हमने क्या किया है, Fi bar is equal to Pi bar, right? By definition, nothing but Y into P. So similar to this one, we have this for ideal gaseous solutions. So ideal gases के लिए Pi bar is equal to Y into Pi, and Fi bar is equal to Pi bar for ideal gases. When you say ideal gaseous solutions, it is Fi bar is equal to Y into Fi. So we are replacing essentially P by Fi for ideal gaseous solutions. इसे डेरिवेशन करके बताया आपको, बट बाय एनालॉजी वी कुड हैव सेड दैट, ठीक है, जस्ट लाइक दिस थिंग वी आर सेइंग रिप्लेस दिस पी बाय फिगासिटी. अल्टीमेटली वी आर सेइंग ना कि फिगासिटी इज नथिंग बट इफेक्टिव प्रेशर. बाय डेफिनेशन दैट्स व्हाट इट इज, राइट? सो इफ यू हैव दिस डेफिनेशन ऑफ फिगासिटी फॉर आइडियल गैसेस, then you can say by analogy fugacity of real gases, ideal solutions rather, is nothing but replacing P with Fi. But we have done this derivation to actually derive this equation and define it for ideal solutions. Right? We have seen this before, right? Ideal gaseous solutions देख लिया हमने, Vi bar is equal to Vi. Let's see. We'll just see this tomorrow. Understand this main thing, Lewis Randall rule, and we're going to use this for deriving non-ideal के लिए क्या करने का. This is going to be basis for all the future derivations which we do. Lewis Randall rule. Take any questions? If there are no questions, we'll stop the meeting. In the meeting.